Alpha wrapping with an offset. Surface meshes are essential components in many geometry processing and computer graphics applications. Most applications require, or at least prefer, input meshes that are combinatorially two-manifold, watertight, and orientable. Unfortunately, many mesh generation methods are imperfect and often produce meshes such as this engine mesh with many issues. Self-intersections, non-manifoldness and spurious boundaries, and complex inner structures. We addressed the problem of generating a watertight and orientable surface triangle mesh that strictly and tightly encloses the input. The algorithm must be robust to defect. In particular, we wish to have a way to control the complexity of the output. This is an example with 3 resolutions, 3 wrap meshes with different complexity. This problem is not new, and some trivial solutions, such as bonding volumes, axis-aligned bonding box, oriented bonding box, or even convex hull exist, but the tightness is insufficient for our needs. Other advanced bonding volumes method exist, such as cages, methods for meshing implicit surfaces, and shrink wrapping methods. Finally, mesh repair methods also exist, but the complexity of the mesh is similar, the output mesh is similar, and the problem is very ill posed. Our approach bridges the gap between a number of existing approaches by combining alpha shapes, mesh carving, and Delaunay-based meshing. We quickly recall these notions. The alpha shape is a generalization of notion of convex hull. A visual analogy of the structure is to think of the ambient space as ice cream and the input point as chocolate pieces. The result of carving the ice cream with a spherical spoon of radius alpha is an intuitive description of the so-called alpha shape. Delaunay carving is a similar concept. However, these two classes have a number of downsides, mainly a sampling of the domain is required and the result is not necessarily manifold. Here is an example of alpha carving in 2D with different values for alpha to illustrate the process. We are carving here the space with empty balls of radius alpha. For large alpha, we are going to fill the cavities and holes and obtain something like this. For a smaller alpha, enables a better approximation as output, and we enter into this cavity while filling the hole. And if the alpha is too small, the carving ball can enter holes, and the result is no longer a closed manifold mesh. Our solution is to perform alpha carving not on the input, but on the offset surface, which is the set of points at given distance from the input. This guarantees that the result is a closed manifold shape for any values of alpha and a distance from input. However, we must now generate points on this offset surface. This is an overview of our algorithm. The main steps, we first wrap from outside, starting from the bonding box. We alternate carving and Delaunay refinement operations while maintaining a valid boundary at all times. The underlying structure is the 3D Delaunay triangulation, which is a well-known safe choice in theory and in practice, and it ties seamlessly with the concept of alpha shapes. Starting from a loose bounding box at the input, we flag tetrahedral cells inside and outside, and the output surface is defined as the boundary between these two types of cells. A carving or traversal operation is performed if an inside cell does not intersect the input. In this example, you see that this triangle does not intersect the input, so we traversed this edge here. The same is for this facet. We entered here, and a facet is said to be traversal if its circumradius is greater than a user-defined alpha. That's an illustration in 2D here. We have an edge adjacent to two triangles. This is the pencil of empty circles. This is the radius of empty circles. And if the minimum here is larger than alpha parameter, we say that that edge is traversable. And we traverse, of course, only if the adjacent cell does not intersect the input. Two refinement rules apply when carving is impossible to densify the mesh and thus tighten the approximation. The first rule is a classic Delaunay refinement insertion, inserting the intersection. So that's an example of this is the edge that is traversable, and we traverse through this direction. We insert the intersection of the dual edge with the offset surface, the pink Steiner point. Rule number 2, if rule number 1 does not apply, and the inside tetrahedral incident to the traversable facet intersect the input, then we insert the point on the offset surface closest to the circumcenter of the inside cell. That's the example of this facet is traversable. This is the dual edge that does not intersect the offset of the input. We thus compute the projection of the circumcenter over the offset surface and insert this Steiner point. Those are the two types of Steiner points in our refinement scheme. This is an illustration in 2D and in 3D. You see that on the left, the color of the Steiner points, depending on whether they are projection or intersections, are blue or green. That's an example with a large alpha parameter. Now, if we specify a smaller alpha parameter, then we are going to enter into the cavity this time. That's the output wrap mesh. In 3D, you see that we start from the bounding box and wrap outside in while refining the mesh and maintaining this property of being watertight, strictly enclosing the input. Let's see some results. The following car model is riddled with all kinds of defects: small holes, panel gaps and overlaps, many multiple open connected components, degenerated elements, and so on. Our method produces a closed manifold mesh on which simulation can be run successfully, computes a wrap mesh here that fills all the holes and gap, is watertight, two-manifold orientable, 500,000 facets in 100 seconds, and this time the simulation, here performed using the SimScale technology, is successful. Our method can also be used as a preprocessing step before sweeping, drastically reducing the runtime. Here the input is a large mesh, 1.7 million facets, has many complex inner structures and all kinds of defects. On this complex input, the computation of the sweat volume by the RMAGS GmbH technology takes 900 seconds. On our output, which has a lower mesh complexity, we obtain a valid mesh with no internal elements, and the sweeping is faster, and the sweat volume is conservative and tight with respect to the exact sweep. Let's now analyze the impact of parameters. First, the alpha parameter, whose purpose is to control the diameter of cavities to be explored. It can be arbitrarily small, and it enables to control the output complexity. That's an example here with a large alpha. Here the B box diagonal divided by 20, divided by 50, and by 150. The final mesh has a higher complexity because at the end it also controls the sizing of the mesh elements. And this value determines, the parameter determines which features will be present in the output. The offset parameter, its purpose is to guarantee a closed two-manifold mesh as output. It can be arbitrarily small, and can also act as a defeaturing parameter at the cost of tightness, similar to shoe shock method. On this bike example, that's the mesh of a NURBS CAD model, which has also defects. That's this example on the left is from a very small offset. We have more than 100,000 facets. And then while we increase the offset, you see that the complexity decreases. So we are sort of defeaturing while wrapping with the margin. When we increase the margin, this time, the area of the offset surface gets larger, and therefore the output complexity increases. Let's have a look at the strength of our methods. The complexity of our algorithm depends primarily on the complexity of the output, meaning that complex inner structures have only a weak influence on the runtime because we wrap outside in and we probe only distance queries. So we query these complex inner structures, but we don't build a transient data structure that is not going to be used for the output. And no internal sampling is required a priori for this method. On this Volvo model, for example, we compute a wrap mesh like this that ignores all inner structures. Thanks to its formulation, making only use of an implicit distance function and basic intersection predicates, our algorithm is immune to the usual defects found in many meshes. On this example, if the mesh input is defect-free, we obtain a mesh like this. If it's full of defects like that, triangle soup with many holes, gaps, overlap, and so on, we are going to reliably compute a wrap, because even if there are degenerated elements, self-intersections, and so on, because we only query distances and intersections on the offset of the input. Basing our algorithm on extensively studied data structures such as the Delaunay triangulation enables us to guarantee, in theory, a number of important properties: termination of the algorithm, validity of the output, because the final surface mesh is extracted from a consistent underlying 3D triangulation. We guarantee that the output is closed and strictly encloses the input, because carving is disallowed when we encroach the input. And we have a bounded one-sided Hausdorff distance, alpha plus offset, because faces of the output have a bounded Delaunay radius. In terms of experimental validation, our implementation, already available in the SIGGRAPH library, uses SIGGRAPH's efficient exact predicates to ensure that theoretical guarantees are met. We perform extensive assertions and tests. All checks are performed with exact computations, and the code is tested on large public data sets such as SIGGI 10,000, GrabCAD, and you can find already the SIGGRAPH component in the on the website of the SIGGRAPH library. In terms of our method is generic, because our implementation follows the SIGGRAPH generic principle. One can easily switch the input representation, triangles, segments, point, and even combine them. So that's an example where we compose a hybrid scene made up of points, triangles, and segments. And this time the algorithm query distances to this hybrid input. For large alpha, which is here 1/100 of the diagonal of the bounding box, we are reliably computing a wrap of the output that fill the holes here, even if here there are a number of polylines, because these are like slices of the input. And if alpha, of course, is very small, like 1/1000 of the input of the diagonal of the B box, then we are going to wrap each polyline in a single tube like that, and the rest, the triangles, within a wrap like this. But everything is still strictly enclosing the input. Thank you very much for your attention. The code is already available in SIGGRAPH, and you can join us at the SIGGRAPH Lab demo in August for an extensive collaborative demo.